Okay, so now we're going to talk about the language of thought hypothesis. And again, I want to make it very clear that we're going to go into some of the nitty-gritty details of the language of thought hypothesis. We're going to talk about some of the desirable properties of a logical language, such as soundness and completeness. I think you should try to understand it, but if you understand it on a sort of a surface level, or if you get the sort of in a nutshell kind of idea, then I think you'll be in good shape. Okay. So to start, the computational theory of the mind asserts that our minds are governed by a logical formal system, much like a computer. But it says nothing about what the structures uh, might look like and how this could explain intelligent behavior seen in humans or a mechanical or how a mechanical process could give rise to meaning. The language of thought hypothesis attempts to answer these questions, right? And so just to zoom out a little bit, give you the big picture, my discussion of language of thought hypothesis is important because it attempts to resolve the issue of how meaning can be derived from a purely syntactic, rule-based, symbol manipulating system. Okay. So the idea is that there's a language in which we think, and it's not necessarily the language we speak. There's sort of a prelingual language that we think in. So these are so these are just some rhetorical questions, uh, like are your language? I'm not going to necessarily answer these questions, but um, you know, are your language like thoughts in English? Are they in your voice? Right? Do they have an accent? How do bilinguals think? Are thoughts necessarily expressed in words? And do words allow you to think of things that you couldn't think otherwise? And again, I'm not going to answer these questions necessarily, but they're just supposed to get you to think about some of these things, right? What is the language in which we think? And so, in order to talk about this, we need to first talk about syntax, the syntax of a formal language. Um, so, and syntax is basically the alphabet of basic symbols of various types, rules for combining those basic symbols into complex symbols, and rules for manipulating those complex symbols. So, like rules of inference. What are the rules of inference? So the basic symbol structures in the mind that carry information are thought to be sentence-like structures in some sort of internal language of thought, which has been termed mentalese. And and the idea is that language of thought is like a formal logical system with its own syntax associated with it. So when we talk about a formal language, right? We're talking about a logical language such as predicate calculus or propositional logic. You don't have to know that. Just know that there are logical languages that exist, formal logical languages. But we're not talking about natural language such as English or Spanish or any of that. And again, in these formal languages, there's a syntax of the language. And that's the symbols that are used, the rules for combining them into complex symbols, and the rules for manipulating those complex symbols. And in this case, although syntax is important, nothing about the syntax is meaningful, right? In the same way that x plus y equals z, it doesn't really mean anything other than what it asserts. It's not saying, you know, x bananas plus y bananas equals z bananas. It's a purely mathematical statement that doesn't actually refer to anything in the real world. And so, in order for these symbols to mean something, whether the statement, whether that statement is true or false in the real world, uh, we need to talk about semantics or the semantics of a formal language. So the semantics provides an interpretation for the symbols of the formal language. So what does each symbol actually mean? Is a given proposition true or false? And every form of language, for every form of language, there's the semantics and syntax. Okay, so in a nutshell, right? Uh, in a nutshell, the language that we think in, according to this hypothesis, the language that we think in must be structured like a formal logical language in which the syntax tracks the semantics. So people who are familiar with logic, this means that the properties of soundness and completeness have been achieved. Um, so the basic symbol structures in the mind that carry information are sentence-like structures in an internal language of thought, which they call mentalese. Logical languages that are sound and complete are languages in which the syntax and the semantics coincide. So soundness occurs if everything that can be proved within the logical system using the rules of that language. Soundness occurs uh, when whatever can be proved by that system is also true in the real world. And completeness occurs if everything that happens to be true in the real world can also be proved within the logical system. Um, so the idea is, the thought I like dogs must be structured in a similar way to the sentence I like dogs, right? So that's the idea. And we might say that uh, that mentalese is like the binary code of our minds, and English, for example, is the programming language that interacts with the system. Okay, so the fundamental question that the language of thought hypothesis tries to answer is how can syntactic representations that can be manipulated physically map on to semantic representations if the brain works in an entirely mechanical way? Now, the language of thought hypothesis doesn't really answer this. It just says that it does and that it has to. So again, we're just going to use an example. I'm going to be a little redundant here, but I think that it's useful and helpful. So in computing the sum of 5 plus 7, the computer uses a mechanical syntactic process on the physical entities that represent the problem. So like the binary code of 101 plus 111, those binary symbols or strings map onto 5 plus 7, which equals 10, or sorry, 12. And so in binary code, 12 is 1100. Um, right, so let's see here. And so the binary system is kind of like the language of thought for computers, and the system has no idea what the binary representations refer to, but it nevertheless comes up with the correct answer. And this is okay because transformations of binary code always lead to the correct numerical answer. So now we're gonna talk about it in the human way, the human mind. So in computing 5 plus 7, the brain uses a mechanical syntactic process on the physical entities that represent the problem. So 5 plus 7 equals 12 is, whatever that is in our language of thought hypothesis. So just like just as there's a binary code for computers, there's a language of thought for humans. And whatever that language of thought is, it nevertheless comes up with the correct answer. And because these transformations in the language of thought always lead to the correct numerical answer, it must be a formal system. Okay. So again, in a nutshell, the language of thought, whatever the language of thought is, it must be a formal logical system in which the semantics of the situation is mapped on to the syntax. In the Bermuda's book, there's really like two paragraphs that I found to be critical for understanding this. So I'll just read those here. Okay, so in sum, beliefs and desires are realized by language like physical structures, that is, sentences in the language of thought, and and practical reasoning and other forms of thinking are ultimately just causal interactions between those structures. These causal interactions are sensitive only to the formal syntactic properties of this physical structures. Yet, because the language of thought is a formal language with analogs to the formal properties of soundness and completeness, these purely syntactic transitions respect semantic relations between the contents of the irrelevant beliefs and desires. Okay. Right. So if we take seriously the idea that the language of thought is a formal system, then this question has a perfectly straightforward answer. Right? Syntactic transitions between sentences in a language of thought track semantic transitions between the contents of those languages for precisely the same reason that syntax tracks semantics in any properly designed formal logical system. Therefore, the language of thought must be like a formal system of logic that has the properties of soundness and completeness. So you're probably going, okay, I know what you said. You said soundness and completeness, but it wasn't enough. Like, what does that really mean? So I'll try to unpack that a little bit more, right? I forget what language this is here, but this is a language that they actually talk about in the Bermuda's book. But if that were, say, the language of thought, that was the syntax of the language of thought. Well, let's say it stands for something semantically, like it has meaning, and that meaning is that at least one person is tall and has red hair, right? So now, if I can prove that in the logical system, if I can prove that in the logical system, and in fact that's true in the real world, then if that's true, then there is a formal system in which the syntax leads to the correct conclusion about the world. All right, so let's try it again. So again, if this soundness and completeness business is a little complicated, just hopefully you can stay with me a little bit longer, and uh, you know, as long as you get the gist, the surface level understanding, that is probably sufficient. But I would try to stick with me, okay? So yeah, two basic results about first order logic and hence about theories that can be expressed in first order logics makes this possible. So we talk about soundness, right? So if P is derivable from delta, then P is a consequence of delta. What does that mean, right? All that means uh, is that when everything that can be proved in a logical system is actually true in the world, right? It occurs when everything that can be proved in a logical system is actually true in the real world. And completeness is if P is a consequence of delta, then P is derivable from delta, right? What does that mean? That just means that completeness occurs when everything that is true in the real world can be proved in the logical system. Okay, so let's use an example. Okay, if the axioms in a formal logical system is if someone is a human, then they are mortal. That's one axiom. The second axiom is Socrates is a human. Okay, so those are two axioms. And then we have a proposition, which is Socrates is mortal. Okay, well, we can use modus ponens here, which is if P and P leads to Q are both true, then Q is true. Well, that just means that, using the rules of the logical system, modus ponens in this example, right? It follows that if Socrates is a human and all humans are mortal, then Socrates is mortal. So we can prove that Socrates is mortal in the logical system. Okay. So the logical system is complete because anytime an argument is true in the real world, it can be proven using the axioms and rules within that logical system. So, Socrates is mortal is true in the real world and could be proven within the logical system. So that makes it, that's one part of it. That makes it complete, I believe. And so the logical system is sound because anytime a proposition can be proven by using the axioms and rules, it is true in the real world. So if Socrates is mortal, could be proven within the logical system, and it is indeed true in the real world, right? Then soundness has been achieved. Okay. And so the brain can only process that the physical manifestations of thought in a mechanical sense, and in the semantic properties of these thoughts must map on to those physical properties. Fortunately, we know that there exists formal languages that are sound and complete, meaning that the syntax can logically track the semantics. Uh, and therefore, right, the language in which we think must be a formal logical language of this type. I put this up here only to say it's I think it's predicate calculus. It's one example of a logical system that is complete and sound, and it's from the book, and therefore maybe the language of thought could be predicate calculus. So in any case, so in the next video we'll talk more about, or we'll talk about the Chinese room argument.